My name is Kasha Alvin Sari, and I'll be taking you through the project slides. The project title is Large Acoustic Models for Visual Scene Narration with Large Visual Embeddings, a project aimed to assist the visually impaired and the blind. So the keywords in this project, number one is the large acoustic models. The planning models trained on massive audio data sets for purposes of text-speech, usually to narrate a scene for an audio output. Then large vision models, these are the planning models that are used to extract features that represent objects. Then objects, you also think about attributes and then spatial relations between the objects and establish contextual awareness in the images. And the images served as input to them, and then come up with high dimension representation of what's actually happening in the image. The large visual embeddings, these are simply the high dimensional representations generated by the large visual models portraying what's actually happening in a scene captured. Then visual scene narration. Visual scene narration, I'll start with, let me first explain scene understanding. So scene understanding deals with analyzing an image or video frame to establish the objects, their attributes, and then the spatial relations between these objects. So it helps a model perceive the overall context, not just the objects in the image, but how the objects are interacting in the environment in a meaningful way. So now visual scene narration comes and builds on this scene understanding to come up with a more natural description. Think of it as a narration of what's actually happening in the scene. Yes, so those are the keywords in this project. So it is known that, of course, vision allows humans to understand and interpret the world through images, emotions, and spatial awareness. Yeah, vision is a very big sense when it comes to the human domains because it simply helps us to see things and get to know how things interact, objects interact, and then draw emotion behind it. An example would be when I see a mother serving their infant a cup of water, an emotion be triggered behind it would be a sign of love. So I would experience the mother passing the love to the child. Then spatial awareness, knowing the relationship between the objects or classes in the environment. So what I've described, the blind individuals actually get to miss the ability to explore and experience the semantic meaning behind visual scenes. So the semantic meaning goes just beyond identifying the relationships between the environment, rather between the objects in the environment. As I'd given an example of the mother and the infant sharing a cup of water, drawing love, that's an emotion a person feels when he sees that. But then the blind individuals miss out on this, miss out on the contextual depth understanding of what's actually happening in the scene. That's simply the semantic meaning. Another example I'd have to give you is when you see a boy holding an umbrella in a rainy day. So it goes just beyond identifying a boy and him holding an umbrella. So the special relationship will be a boy is holding an umbrella. It goes down to know why actually the boy is holding the umbrella. And this is just simply because it is a rainy day. So they want to feel protected from the rain. So those emotions, the blind individuals get to miss out on them simply because they can't see and feel and experience the visual scenes. So then the existing acoustic tools aim only to describe and identify objects, not just even in full context, and they also lack out on the emotion of a scene, as I already explained. So there's a growing need for intelligent systems that translate vision into meaningful sound for the visually impaired. So as I told you, vision captures context and also meaning in their surroundings. So you get to know why actually things are happening this way in the environment. So the blind individuals miss out on this ability. So the current assistive tools, they don't only just rely on identifying objects and also relationships, but they don't establish the meaning or the emotion in a scene captured. So this work integrates large visual embeddings extracted by large visual models, and they represent semantic understanding of what's actually happening in a scene, going just beyond identifying objects and the relationship between objects, but knowing why objects are doing or interacting in the environment in this way. And this helps an individual who is blind to build on an emotion and be like, oh, this is actually happening like this. Yeah. So the system allows the blind users to experience the world's meaning through bridging the gap between what between seeing and also understanding what's actually happening in the environment. And then at the end of it all, they have large acoustic models, as I told you. These are trained on massive audio data sets, and they translate visuals to an expressive narration derived on an emotional identified of the scene. So these are some of the related works. One on this paper is called AutoSite, and they built a context-aware interactive system that leverage multimodal large language models with a real-time visual analysis that will capture the vision and then pass it to a large language model and then generate a dialogue-based interaction. So it was on a limit. The limitation it had no continuous scene narration and also lacked to build on the semantic understanding that lied beyond what was actually captured in the scene. Another paper was the Ocam My Eye. It was a wearable device that could actually print text faces and also objects into speech using computer vision. So set acoustics to derive what was actually seen and then put it out into audio. So the imitation it was built on focusing on discrete objects rather than having a semantic scene, understanding what's actually happening in the environment. The other one was the scene to audio by Group to 2025. And this was entirely about distant scene representation, representing what's actually happening in distant scenes. The limitation it had, it lacked understanding of the depth understanding what's actually happening, and this built on lack of semantic understanding what's actually in the scene. So it built on neon. It was limited on distance scene represent what's actually happening in the scene at a distant level, but then lacked bringing out the meaning of what's actually happening in the scene. Then another investigation, that paper was an investigation into using acoustic touch to assist people who are blind. So this was an acoustic-based system that helped blind users allocate objects in the environment and pass down output or feedback through audio, hence acoustic. But then this only focused on object localization, but lacked semantic understanding and context-aware narrations of scenes. So the audio output or the acoustics that were given was only identifying objects, but then lacked the semantic understanding of the spatial relationships between the objects and how they interact in the environment, and then also a narration of what's actually happening in that scene. So the domain problem, of course, we deal with assistive technology for the visual impaired and blind individuals. We want to help these blind people to experience things that actually happening, things that they cannot see, experience through understanding meaning of what's actually happening in the environment. So this just goes beyond just identifying objects and their relationships, but knowing why there is a relationship, what's actually happening, what is causing an object to interact with another object in a scene. So blind people are missing out this, and this work aims to fill this gap. So we want to transform complex visual scenes. Of course, complex visual scenes have semantics, semantics that go beyond just identifying objects and also the relationship between objects, but understanding why objects are interacting in that way. Yes, and build emotion and help these blind people experience. So we do this by transforming the complex visual scene into high dimension embeddings, which are the large visual embeddings generated by the large visual models. And these capture the semantic relationships, the more depth understanding of the scene, and what align them with the textual embeddings to feed into a large generation model that will be able to come up with a more descriptive narration of what's actually happening in the scene. So what a system that can be able to capture the rich semantic and spatial representations from the visual scenes, and then align these visual and textual embeddings, then generate a coherent and expressive language generation that would be outputting audio for the blind person, visually impaired, to feel, to experience what's actually happening without actually seeing it. So the research questions and their objectives is, how can large vision models capture both semantic and spatial features from complex scenes? So realize we need to design and implement a large vision model capable of extracting deep visual representations from images using a visual encoder. Then which techniques can we use to build to improve the generation of, we want a natural human-like contextual coherent narration for the blind, such that they enhance awareness of what's actually surrounding them. So we want to build a large generation model that takes in the large visual embeddings and then builds coherent and then context-aware narratives based on the aligned embeddings from the large vision model. And then how can we align these visual embeddings to ensure accurate semantic correspondence between images and descriptions? So that research objectives, develop a visual text alignment model that bridges the gap of what is actually seen and what is actually spoken out. So ensuring the semantic understanding in the image captured is the same thing that is passed to the semantic understanding of what is actually described happening in the scene. So the research contributions and outputs I developed a large vision model, of course, capable of extracting the large visual embeddings or the extracting the high dimensional visual embeddings from the input images of the scene captured in terms of input images and also the video frames. Then also developed a visual text aligner that converts the visual embeddings into text tokens that are fed into the GPT-2 as input, and also fine-tune a GPT on the visual storytelling data set for the purpose of generating short descriptive stories for the blind, based of course on the scene captured. Then the methodology is simply like this. We have an image input or the video frame fed into the large vision model. These are the eyes of the proposed methodology. This has the scene understanding, generates large visual embeddings, but you get to realize that it was trained on an image text pair. So it generates both image embeddings and rather visual embeddings and text embeddings, but it generates them in terms of different embedding space. So the visual embeddings are in 748 visual embedding dimensional, then the text embeddings are in a 1024 embedding space. So we need to have a projection here. That's where it comes to align them into the same dimension space, which is 1024, generate the large visual embeddings. So you get to know the large generation mode expects text tokens as the input. So you need to have something to align the large visual embeddings to text tokens that are understood by the large generation model. This is where I have the visual text aligner that converts the large visual embeddings into text tokens that are fed into the large language generation model to come up with a scene narration, what's actually happening in the scene. And then at the very end of it, we're having an acoustic model to come up with expressive narration in audio of what's actually happening in the scene. This is the overall proposed methodology. Then the data set that was used to train the large vision model was the common objects in context for 2017. A large data set, of course, used for object detection, segmentation, and image captioning over a size of 118,000 training images, 5,000 training validation images, and 41 testing images. Some of the EDA visualizations we have here is the distribution of super categories in the data set, which is I see animals and sports and also types of food dominating. The top 10 most frequent categories are the person, car, chair, etc. Then for the GPT, it was trained using the visual storing dataset, designed for storytelling, full narrative generation, and these are some of the EDA visualizations. It has over 1,020,000, over 12,000 stories in the training split. Then in the validation, they've split has over 2,000 stories. Then the test, it has below 2,000 stories. Then sentence count per story, you could clearly see that they lie between 4 to 6 sentences per story. Yeah. And you get to know that each story contains over 5, contains 5 images, including descriptive and contextual sentences for storytelling tasks. Then models, large generation had the GPT medium, then large acoustic model doing with a core text to speech, then large vision model using the vision dictation as the vision model. Then the experimental results for the VIT could, of course, as I telling you, the image embedding shape was 1 to this, and text embedding shape was also 1024 dimension after the projection head, and then I could use the cosine similarity to compare the image and text embedding, and it was 7 out of 10, which was actually a positive alignment or similarity, and the constructive dose was actually 0. So we used it on unseen data to see if the model was not actually overfitting, and it captioned it. We used the blip captioning on the VIT to the image embeddings to the blip to come up with a caption what's actually in the image. So it was like the woman is smelling while drinking wine with a man, which you clearly see it's nearing, but it needs more fine tuning to come up with a better captioning. But then feeding the embeddings after the video text alignment, the generated story was a family picnic with children playing with other kids was out of fun. So you realize the GPT mode was also having that part of fun and also gathering of people. So it was that it needed the visual to text align needs further fine tuning to give the GPT model so it produces a better narration. Then some of the limitation dimension mismatches, we built a projection head, align the image text embeddings, visual text alignment, we train the alignment to map visual embeddings better with text tokens. Limited GP, we had of course to use a smaller batch size during model training. Then some of these are references. These for the bootstrapping language image pre-training with frozen image encoders for the large vision model, and of course also the large language model. Then also the seeing AI, of course, that's a Microsoft product. And then also the acoustic scene classification Yes, and then also the cognitive assistive embedded for people with visual impairment. This also has acoustics at the end as the output to describe what's actually happening in the scene using IoT. Thank you very much. That was the end of my presentation.